Hello everyone, welcome to the channel Learn Math with Shobita. Today I am discussing some questions from linear algebra. First question: the rank of 4 by 4 real matrix with exactly 5 non-zero entries cannot be option A 1, option B 2, option C 3, option D 4. Let us analyze the question. Given matrix is 4 by 4 matrix and it has 5 non-zero entries. So the entries will be like this. Suppose the entries will be like this, 4 entries, and another entries will be like then it has maximum number of linearly independent rows will be 2 and its rank will be 2. Suppose the matrix 4 by 4 matrix with 5 non-zero entries 0 0 0, and here it is 0, here it is 0, here it is suppose it is like this, then its rank will be 4. And suppose the matrix 4 by 4 matrix with non-zero entries non-zero entries like this, then here the rank will be 3. So there is the possibility 2 3, the rank can be 2 4 3. Therefore the rank of a matrix with the 5 non-zero entries cannot be 1. So option A is true. Next question: let A be an n by n nilpotent non-zero real matrix, then option A in plus A is invertible, option B in minus A is invertible, option C A is invertible, option D A is diagonalizable. So given A is a nilpotent matrix, so its all eigenvalues are 0. So A is invertible, this option is wrong. Also it is not diagonalizable. We have, if A is a nilpotent matrix, then both in plus A and in minus A are invertible. So option A and B are true. Next question: let A be a 4 by 4 real orthogonal matrix with the determinant equal to -1. Then the determinant of I power I4 minus A is option A 0, 1, 2, 5. Okay, these are the options. So how we can solve? Given the matrix is 4 by 4 matrix and it is orthogonal, also its determinant is -1. Determinant of I power 4 minus A we have to evaluate. Okay, we know that product of eigenvalues is the determinant of A. Okay, so if lambda 1, lambda 2, lambda 3, lambda 4 are eigenvalues of A, then 1 minus lambda 1 into 1 minus lambda 2, 1 minus lambda 3 and so on, 1 minus lambda 4 are the eigenvalues of I4 minus A, I minus A. Given determinant of A equal to -1. So the eigenvalues, possibilities of eigenvalues are either all three eigenvalues are 1 and one eigenvalue is -1, then their product will be -1. Then the eigenvalue of I minus A will be 1 minus lambda 1 equal to 0, 1 minus lambda 2 is also 0, 1 minus lambda 3 is also 0, 1 minus lambda 4 will be 2, but the product, their product we got 0. So determinant of I minus A is 0. Now other possibilities are one eigenvalue is 1, other 3 are -1. Suppose complex eigenvalues exist, then they occur always in the conjugate pair. So if 1 is the one eigenvalue, then if I is an eigenvalue, then minus I is also eigenvalue and -1 is another eigenvalue. So in all the cases we got determinant A of I4 minus A is 0. So option A is correct. Next question: let A is given by 3 by 3 matrix, 12, 24, 5, x 6, 2, minus 1, minus 2, 3. The value of x for which the matrix A is not invertible is. So we have to find the value. See, without calculating the determinant, we can check how. Given we have to find the value for which A is not invertible. We know that a matrix A is not invertible if determinant of A equal to 0. So when will be the determinant is 0? See here, in the first column the entry is 12, in the second column it is 24. It's double, 12 into 2, 24. And here in the third row, in the first column, first entry minus 1, and in the third row second entry is minus 2. So this entry is obtained by multiplying 2 to first entry. Therefore the x will be 6 by 2, 3. The value of 6, if it is 3, then two columns are linearly dependent and its determinant will be 0 and A is not invertible. So if for x equal to 3, the first two columns are linearly dependent and hence determinant is 0, therefore A is not invertible. So value of x is 3. Without calculating the determinant, we can find the value. Okay. Next question. Let A equal to 2 by 2 matrix pi p q r, where p, q, r are rational numbers. If determinant of A equal to 0 and p not equal to 0, then the value of q square plus r square is 2, option B is 1, option C is 0, cannot be determined using the given information. So here determinant of A is pi r minus pq, that is given, it is 0. So we get pi r equal to pq or q is equal to pi r by p, given p is not equal to 0. Now q square plus r square, we will get this. So I think the option D is correct, that is cannot be determined using the given information. Q square plus r square, they have not given the value of p, so we cannot evaluate. Okay. If any changes in the answers, please give your answer in the comment section. Next question. Let A equal to ABCD be a 2 by 2 real matrix with determinant A equal to 1. If A has no real eigenvalues, then see the options. I will not read the options. If you want, please pause the video and see the options. So what we have to do, we have to check what is A plus D whole square. Okay. Given it is a 2 by 2 real matrix and determinant is 1, it has no real eigenvalue. Okay, since it is a 2 by 2 matrix, it has two eigenvalues. Since it has no real eigenvalues, all the two eigenvalues are complex. If a complex eigenvalue occurs, then it always occurs in conjugate pairs. Okay, so since A is a 2 by 2 matrix, it has two eigenvalues. Both are complex because it has no real eigenvalue. Okay. Also we know that product of eigenvalues is equal to determinant of A, and trace of matrix is the sum of the eigenvalues. Suppose lambda 1 and lambda 2 are two eigenvalues, then determinant of A will be lambda 1 into lambda 2. This is for 2 by 2 matrix, and trace A will be lambda 1 plus lambda 2. Okay, trace A is A plus B, determinant A is AD minus BC. Suppose x plus iy is an eigenvalue of A, then x minus iy is also an eigenvalue of A, because if a complex eigenvalue exists, then it always occurs in conjugate pairs. Okay. Now its product x minus iy into x plus iy, you will get it is 1. So after calculating, you will get x square plus y square equal to 1, because they have given determinant of A equal to 1. Also sum of eigenvalues is the trace. So adding these values, I get 2x equal to A plus D. Now A plus D whole square is equal to, evaluating, I will get this is 4x square. But here we have x square plus y square equal to 1. This implies x square is less than 1. So applying this, I get A plus D whole square is equal to 4x square, which is less than 4. Therefore, option A is true. Next question. Minimum of dimension of the intersection of two 7-dimensional vector subspaces in a 12-dimensional vector space is. Option A 0, option B 2, option C 5, option D 7. Given two intersection of two 7-dimensional subspaces. So let W1, W2 be two subspaces having each having dimension 7 and dimension of V equal to 12 they have given. Then we have the formula dimension of W1 plus dimension of W2 is equal to dimension of W1 plus W2 plus dimension of W1 intersection W2. Okay, we have to find the minimum value of dimension of W1 intersection W2. Since W1 plus W2 is a subspace of V, dimension of W1 plus W2 is less than or equal to 12. Also, both W1 and W2 are contained in W1 plus W2. So, dimension of W1 plus W2 is greater than or equal to 7. Okay. So, the maximum possibility of dimension of W1 plus W2 is equal to 12. Therefore, minimum of dimension of W1 intersection W2 will be equal to 14 minus maximum of dimension of W1 plus W2. That is 14 minus 12, you will get 2. Okay. So, minimum value is 2. Next question. Suppose A, B and C are 3 by 3 matrices with the determinant of A equal to 3 and determinant of B equal to 3. Then determinant of 2C A square B transpose into CA inverse into B is option A 54, option B 216, option C 27, option D 172. So how to calculate this determinant? Okay, there is a simple trick to evaluate such type of determinant. Here it is given 2, constant 2 is given. So how? Let us see. Okay, according to properties of determinant of Ka is equal to K to the power n into determinant of A if A is a n by n matrix. Okay, therefore determinant of this given matrix will be equal to 2 cube into determinant of the remaining. Okay. So determinant of CA square B transpose. Okay. Therefore, the determinant of the given expression will be multiple of 2 cube. 2 cube is 8. So which number is the multiple of 8? Let us check. Okay. So here 216 is the multiple of 8. Therefore, the value of this determinant is 216. Others are not divisible by 8 and 216 is the only number which is divisible by 8 here in this given option. So option B is true. If you want, we can check using the determinant of property, that is determinant of AB is equal to determinant of A into determinant of B, applying this, and this will be a calculation with the complicated. So this is the simple one. Next question, the dimension of the vector space over R of all 5 by 5 upper triangular matrices with the complex entries is. Okay, so we have to evaluate the dimension of a upper triangular matrix. What will the dimension of an n by n upper triangular matrix? So for n by n upper triangular matrix, here diagonal entries are non-zero and the entries above the diagonal are also non-zero. Okay, here these terms are 0. Okay, so what will be the dimension of upper triangular n by n upper triangular matrices? Here it is in the last row, you will get is only one non-zero entry. In the row above the last row, there are 2 entries. So 1 plus 2 plus and so on plus n. Sum of first n natural numbers, you will get this is n into n plus 1 by 2. This is in general for n by n matrix. Okay, but here they have given complex entries. So since the entries are complex, for each entry Aij we require 2 entries, 2 real entries x and y, x plus iy. Okay, so for n by n complex upper triangular matrix, n by n complex upper triangular matrix, the dimension will be equal to 2 into n plus 1 into n by 2. So this is n into n plus 1. Okay, here they have given n is equal to 5. Therefore dimension will be 5 into 5 plus 1. 6 into 5 is equal to 30. So option A is the correct answer. Thank you friends. Please share and subscribe the channel. If you have any doubt, please comment in the comment section.